Okay, good morning, everyone. Thanks for staying up to the very last presentation of this conference. My name is Andrés Díaz. I come from the University of Burgos in Spain. And today I will present this work, this experimental and numerical work that we have done in collaboration with our colleagues from the University of Oviedo. And I will focus on the modeling part of these experimental results for this Duplex 2205 stainless steel. I will skip, everyone is tired, so I will skip the classical motivation and even the outline. This is the experimental results that we are going to interpret and to use to build a kind of predictive model. We are studying a 2205 duplex stainless steel in the hot roll condition. So as you can see, we have a strong anisotropy because the austenitic phase is elongating along the rolling direction, as you can see. And we are following the ASTM G142 standard, and we are choosing the notched tensile specimens. You can see the experimental results that we are obtaining for those two orientations that we extract from the plate, longitudinal and transversal. And we find, due to this anisotropy, that the reduction in the notched tensile stress, according to this standard, is stronger in the transverse direction because of these anisotropic effects. All of the tests are done in situ in this autoclave that we have in Burgos, integrated to a universal testing machine. Pure hydrogen, I can give you more details about the experimental facilities if you want. And a key point here is that we have a slight influence of the pressure after higher pressures. So we expect a kind of saturation of some interface or defect, as we will discuss later. And another point is the dilemma of the hydrogen penetration distances, because as you probably know, the diffusion in this kind of steels is very, very low. So for the testing times that we are obtaining following the crosshead displacement rate of this standard, tests are very short, maybe less than 5 minutes for the strongest embrittlement. So for this very short penetration, why we are obtaining this relatively high embrittlement. So we have two goals. First of all, to interpret all of these topics that I will raise. And finally, our ultimate goal is to develop a predictive model to design new infrastructures with this material. And the model that we are going to use, it's called HPF. It's just a phase field fracture model informed by a hydrogen transport model. We are using, I will skip the details of the phase field fracture model, but this is the key point in the phase field fracture model, as in many other damage models, that is capturing the reduction in mechanical properties. It's just the reduction in the fracture energy or critical strain energy release rate. And I call that the holy grail in high hydrogen embrittlement modeling, because we have a lot of discussions. We are not coming to an agreement if we have to be inspired by DFT calculations based on fracture mechanics testing. We can use a phenomenological law and so on. I'm open to any suggestion about how to improve these kind of laws and how can we be more mechanistic. But we choose this linear reduction because we are inspired by DFT calculations that show that you have a linear reduction as a proportion of coverage of an interface. Okay. In our case, we are not using a general coverage. We are using the occupancy of a kind of trap. In our case, since we are seeing that after a high pressure, we don't observe a stronger embrittlement, we are assuming that embrittlement must be triggered at the very strong retention sites. And from literature, we deduce that they should be austenite ferrite interfaces. Of course, this is also open to new interpretations. And finally, we are not fitting this degradation function, this degradation factor from DFT. We are fitting this value experimentally, and it should be dependent on the delamination. You can see here a cross-section of the notch specimen. We have very strong delamination, so this degradation factor should be dependent on the orientation. So the Chi degradation function factor will be fitted through testing, and the coverage, the occupancy of the interfaces will be locally calculated using finite element modeling, a local hydrogen transport model. This is the overview of the transport model. This is not our idea. Our idea was to combine both classical frameworks, the framework from Sofronis and McMeekin, where you can capture the influence of hydrostatic stress and also of trapping, and the modifications that Turnbull and Hutchins did to account for the particularities of dual microstructure with a very low diffusivity, the austenite, and very high diffusivity, the ferrite. Two main modifications: we don't use a scalar diffusivity, we use a diffusivity tensor, and this component for its in this diffusivity tensor are related with the diffusivity through the ferrite and also through with the tortuosity of the path. For example, in the longitudinal direction, if you remember, is the rolling direction, we expect elongated austenite grains, so the diffusion path for the hydrogen will be more straight. So the omega for longitudinal direction, this tortuosity factor, will be closer to 1 because we are close to the straight path. Okay, and we are considering 3 topping sites: hydrogen retained at the austenite phase, at the interfaces, or at other general defects within the ferrite phase.
We are all organized.
I want also to mention that you have to be thermodynamically consistent to model your hydrogen uptake. So you can use a kind of Siebert's law, but using fugacity and including the effect of hydrostatic stress on this uptake. We have a lot of parameters, but it's easier than it seems. We are assuming some parameters from ab initio calculation, especially for diffusion through iron. We are using some theoretical and values from literature for the solubilities and for the density of FCC sites, of austenitic sites. And after that, we are obtaining these tortuosity factors that I was talking before, and the density of interfaces using a geometrical 3D reconstruction that I will show later on. And finally, the energetic parameters for both trapping sites that are missing, the interfaces and the defects are ferrite, are going to be fitted using thermal desorption. This is the 3D reconstruction I was talking before. This is very simple. We are just taking slices from the optical microscope, 3 orthogonal slices. We input these slices into a reconstruction code, which is using optimization of the descriptors for this geometry. And you get a 3D reconstructed geometry that is represented your real unit cell for this elongated microstructure. We put this 3D unit cell into COMSOL multiphysics with a simple diffusion model, and we are able to calculate the tortuosity factors, just accounting for the percolation and the connectivity of each phase. As we were expecting, in the longitudinal direction, we are closer to 1, and in the thickness direction, we have a very low value because it's very tortuous. The path is very tortuous. Finally, we are fitting the values of the trapping energies and the density of defects in ferrite. And all of these steps have been performed in the University of Oviedo. And the first step that we have done is to find the trapping energies fitting the TVA profiles. And we identify 2 main peaks. One peak, the lower energy peak, was attributed to the defects at ferrite, and the strongest defect to interfaces. I'm putting this subscript Kissinger because actually we don't trust the Kissinger results. This plot that maybe you are familiar with, we have demonstrated, and many authors have numerically demonstrated, that the Kissinger plot is underestimating always, especially under certain conditions, but it is always underestimating the trapping energies. So we are not fitting, after that, the second stage, we are using these room temperature desorption curves in 2 orientations, and we are fitting not the trapping energies, but the error that Kissinger is making in this fitting. So with these 2, the desorption curves in the T and S direction, we are fitting the Kissinger error and also the density of trapping sites at ferrite. We can fit each orientation, and we can also do a combined fitting. And this is very nice because the combined fitting is very close to the individual fitting for each orientation. This means just that the effect of orientation in these desorption curves is just explained by the tortuosity, because the trapping features, the trapping energies and the trap density should be independent of orientation. So since both fittings are very close, the global fitting and the individual fitting are very close, we can say that this is more or less accurate. Okay, just to finish, I'm going to show you some results in the complete 3D and 2D model of these notched specimens. To begin with, we can plot the diffusion distances in a 3D model, including the stress-assisted diffusion and trapping. But here we are not including phase field, only diffusion and mechanical modeling. And this is not to scale, of course, because as you can see here, the distance, the penetration distance is very low, 10 to 15 microns, close to the maximum force. So we have a very small penetration with these trapping and diffusivity parameters. This is in the longitudinal orientation of the specimen, and we can observe both diffusion into the T and S direction. Of course, since the tortuosity through the T direction is faster, we are going to observe higher penetration distances, and the same for the sample in the transverse direction for the hot roll plate. You can see here that the penetration distance between L and T are not very different, because actually you have to think that the penetration distance is proportional to the square root of the diffusivity. So the increase in penetration distance, depending on the orientation, will be proportional to the square root of the tortuosity. Okay, let's move to the next case study. In these simulations, you can observe that we don't have radial symmetry, we don't have axis symmetry, but the penetration distances are very small, so we can assume, to simplify the fitting of the mechanical model, because this is very challenging from the computational side. As you can imagine, with these very short penetration distances, we need very, very fine mesh. So it's challenging to do it in 3D, but we can simplify for axisymmetric model. And if we do that and fit the phase field model that I was talking before, we can nicely fit the reduction in the notch tensile strength for both the longitudinal and the transversal direction. And first of all, we can observe that the longitudinal value the degradation factor is lower than the transverse degradation factor. So this embrittlement is depending on the orientation, as we were expecting. And also, you can see that we are not capturing 100% this slope in the pressure influence. So that means that our fitting could seem very nice, but maybe we need a lower binding energy of defects to interpret this embrittlement. Because if the binding energy is lower, we are going to have this higher slope. Also, we need to explore in future research what's happening between this 0 and 35 bars, because probably we are going to be surprised and we are going to have a strong embrittlement even for very low pressures. This is also what we have to do. And finally, an interpretation of what's happening locally. At the beginning of the load, you can see there at the left picture that we have a very steep hydrogen concentration at the ferrite sites, but because of this high binding energy of interfaces, all of the interfaces are saturated near the notch tip. So we have interfaces saturated, and we have a strong reduction in the critical fracture energy. It's like we have a very small stress concentrator, a very initial stress concentrator near the notch tip. So this is challenging because we need very small elements. We are having some numerical oscillations, but we can observe here that this is just enough, only less than 10 microns, to evolve into a hydrogen propagation fracture. Okay. And just to conclude, the model captures anisotropy both in diffusion and in fracture, because we are fitting the degradation factor depending on the orientation. We are assuming that the embrittlement is triggered by this occupancy in the trapping sites at interfaces, but we are not sure about that. We are doing more microstructural characterization to give more insight on this. And we have shown a simplified calibration using axisymmetric models, including not only diffusion and trapping, but also phase field. Just a quick mention of our ongoing work. We are also trying to explain the influence of triaxiality of this. When you reduce the notch radius, you are observing a higher embrittlement. We are also calibrating the model with a 3D complete finite element model, which is challenging from the computational point of view. We are doing fracture in situ also, in this case with C and B. And we are also exploring how it's behaving, this same material, 2205, when you print it in SLM, because the interfaces, of course, are going to completely change. We are observing a dendritic microstructure, so maybe it's not so embrittle as the conventional 2205. So we'll see. And that's all. Thank you for your attention.